Hello, my name's Conrad. I'm an engineer on the Swift language team. And today, I'd like to introduce you to a new interoperability effort that we've kickstarted earlier this year, SwiftJava interoperability. We're excited about interoperability because it broadens the range of applications where we can use Swift. Using interop, we can incrementally introduce Swift to existing code bases written in other languages. We don't have to do big, risky rewrites, and instead, we can just add a new feature or replace an existing feature with Swift without touching the rest of the existing codebase. We can also reuse existing libraries implemented in other languages. We can make libraries written in Swift available to them instead. And the way we approach interoperability goes beyond just the language as well, as we integrate with build tools that are most appropriate for each ecosystem, like CMake for C or C++, or Gradle for Java projects. Interoperability with C languages has been a first-class feature of Swift since day one. It enabled Swift to seamlessly integrate with the existing Apple developer ecosystem and eventually become the primary language for developing on these platforms. 2 years ago, we introduced the C++ interoperability effort, which enabled seamless blending of C++ and Swift libraries in a single codebase. This opened up many possibilities for using Swift in even more places. To learn more about this, you can check the Mixed Swift and C++ session from WWDC25 or this year's Safely Mixed C, C++, and Swift session. When we talk about interoperability, there are two directions we can focus on. First, we can be writing an application primarily in Swift and call into some code written in Java. Or we can focus on making Swift easy and efficient to call from Java instead. Swift's Java interoperability supports both these directions. The tools and techniques we use in each direction are slightly different, but you may find yourself using all of them together in a single project. Before we jump into specific examples, let's revise the differences between the Java and Swift runtimes. Then we'll explore 3 practical examples of putting Java interoperability to work. First, by using Java's existing native methods feature. Then we'll explore how we can make an entire Java library accessible to Swift. And finally, we'll explore the opposite direction and wrap an entire Swift library for easy consumption by a Java project. Let's start with comparing the two runtimes. After all, the Java runtime is very different than any other native language Swift already has interoperability with. Although, if we zoom out a bit, we could actually say that Swift might be the most similar native language to Java out there. Both languages offer classes, with a similar inheritance model. Both provide a way of automatic memory management, largely transparent to the developer. They both offer a generic system that's pretty similar as well, although represented differently at runtime. And finally, Swift errors can be thrown, just like Java exceptions, although again, the amount of information they carry at runtime is slightly different. The important thing is that, by carefully choosing how we're going to interact with those features, we're actually able to express most APIs from one language in the other. Now that we've reminded ourselves of the differences and similarities of these languages, let's jump right in and see how we can extend an existing Java application. We'll start really simple and just focus on implementing a single function in Swift. In order to do this, we'll use the Java language feature called native methods. Java native methods are part of the Java Native Interface API, also known as JNI for short. JNI has been part of Java since 1997, it's before the iPod, and it's been designed as a way for Java to interoperate with native code. It is often used in order to achieve performance goals, by moving work off the Java heap, or in order to use native libraries which don't have a Java equivalent. It is still one of the primary ways Java and native code interoperate, and the APIs have not really changed ever since, so it only makes sense for us to start our exploration with JNI itself. In order to familiarize ourselves a little bit with JNI, let's follow the traditional steps one would have to follow to use JNI without any support libraries or tools. On the Java application side, you'd define a native function, which we'll implement using native code. In order to illustrate how JNI deals with passing objects to native code, we're using the uppercase integer types as arguments and return type of this function. Unlike primitive int values, these are Java objects, and we'll have to work with them accordingly. Then you'd have to use the Java compiler with a -h flag on any files that contain native methods. This would result in a C header file that contains C function declarations that the JVM will attempt to invoke when the corresponding Java native method is called. The declaration is a pretty verbose name, Java com example, JNI example compute, which matches the package, class, and method name of our native method. It accepts something called the JNI environment and JObjects parameter for the this reference of the Java objects we're calling the method on, and all the parameters of the original Java function declaration. Finally, you'd actually implement this function in the native language of your choice, which for us would be Swift. Oh, that's a lot of code, isn't it? All the boilerplate is really drowning out the actual logic implementation, which is over here. It isn't just noise. It is numerous opportunities to get something slightly wrong, which would then result in a fatal crash. In summary, JNI is a well-supported way to call native code from the JVM, but it's also very difficult to use correctly. To make method implementations performant, we may need to involve caching and other techniques which further complicate the code. There's additional build steps and C headers to worry about. Manually matching all the method signatures and magic strings is really error-prone. And we also have to carefully manage object lifetime of any created or received Java object. So doing JNI without additional support is possible, but it's not a great experience. Which brings us to SwiftJava, the new home of the Swift and Java interoperability effort. We're building SwiftJava to provide Swift and Java developers a flexible, safe, and performant way to interact between those two languages. SwiftJava consists of a few pieces, but you may reach for independently or together. First, a Swift package, which provides the JavaKit library and macros which make dealing with JNI code, like we've shown on the previous example, much safer. Next, we have a Java library called SwiftKit. It helps Java applications deal effectively with Swift objects. And finally, the SwiftJava command line tool and other build system integrations, like for example, the SwiftPM plugin, or even the work-in-progress ways to integrate with popular Java build tools such as Gradle. Let's redo that last example, but this time we'll use the tools provided by SwiftJava. Instead of the Java compiler, we'll use the SwiftJava command line tool to generate the necessary bridging. We need to provide it a module name where the generated sources should be written and some additional configuration. In more complex projects, this would be triggered by a build plugin in SwiftPM or a different build system you're using. The result of this workflow is a Swift file containing declarations that describe the imported Java class. If the Java type had any member methods, they would appear on the corresponding Swift type as well, allowing us to call back into these Java functions from Swift. And finally, the generated JNI example native methods protocol contains all the native methods that we can implement for this type. This serves as a replacement for the C header we were using before. To actually implement our native compute function, all we need to do is write an extension on the generated JNI example class and conform it to the JNI example native methods protocol. We also have to annotate it using the Java implementation macro, which is provided by JavaKit. Next, the compiler will assist us in implementing the correct required function signature. The only additional thing to remember is that we need to annotate it using the Java method macro, which handles some further JNI details for us. Thanks to SwiftJava, our method implementation became much simpler now, and we can just focus on our business logic. What's even better though, is that now since we're in Swift, we can use any Swift library we'd like. For example, I might want to use a native implementation of some cryptographic algorithm. The Swift ecosystem happens to have a great library for that, and I can import the crypto module and, for example, compute the SHA-256 hash for the passed-in data. You may remember the list of issues we had in our previous JNI implementation. Most of them are not as much about JNI, but about how difficult it was to use correctly. Thanks to SwiftJava's approach to JNI, we can avoid a lot of the boilerplate, and the resulting code is much easier to maintain and save by default. We don't need to interact with C headers at all, and instead we can rely on well-typed generated function signatures. This saves us from mistakes, which can take a long time to debug. And finally, object lifetime management is much improved in comparison to manually writing the glue between the languages by hand. This is crucial for writing memory-safe code crossing language barriers. So overall, it is much nicer and safer to do any kind of JNI interactions with SwiftJava rather than writing it by hand. But we're just getting started, and SwiftJava has lots more to offer. Next, let's consider a situation where we'd like to use a Java library from Swift. We'll be using the same SwiftJava tool again, but this time, let's focus on how we'd approach importing a whole existing Java library, not just a single type. For example, let's say I'd like to use the popular Apache Commons CSV Java library from Swift. Not only do I need to find the library itself, but also all of its downstream dependencies. Dependency resolution gets complicated very quickly, since Java libraries often have many transitive dependencies, which also have their own dependencies, and so on. Thankfully, SwiftJava can take care of this for us. All we need to do is prepare the artifact coordinates of the library we'd like to use. You can usually find them easily by searching online. You can ask a Java developer friend on your team if you're not sure yourself. The dependency will be expressed as a triple of an artifact ID, identifying the specific artifact, a group ID, identifying the organization publishing the library, and a version number. Next, we'll make use of SwiftJava's Gradle integration, which is a popular build tool and dependency manager in the Java ecosystem. In order to express this dependency to Gradle, all we need to do is put colons between these three values. In this way, we've just formed a dependency descriptor in a format Gradle understands. Now that we know the dependency coordinates, we have two options to choose from for how to download and wrap them in our Java Apache Commons CSV target. The first method is to use the SwiftJava build tool plugin. Inside our target's SwiftJava config file, we'd add a dependencies section, listing all the root dependencies we'd like to resolve. This is quite nice. Now the plugin will automatically invoke Gradle to resolve Java dependencies whenever we build our SwiftPM project. However, SwiftPM enforces a security sandbox that makes sure build plugins cannot access arbitrary files and network. So if you'd like to use this approach, you can choose to disable the security sandbox when building the project. This may not be viable in all environments, so here's an alternative approach you can take. Instead, we can use the SwiftJava command line tool's resolve command. By passing it a module name that contains the config file, the tool will resolve the dependencies and write the resulting class path to a file. Since this is performed outside of the SwiftPM build, we don't have to disable the sandbox. It does mean, though, that you would have to manually trigger the dependency resolution like this before building your project. This is a trade-off, and you can choose whichever model better suits your workflow. Either way, now we're able to use the Java library from Swift. All we need to do is import JavaKit and the Java Apache Commons CSV modules. Then we start the JVM inside our Swift process in order to run the Java code. With that, we're ready to use Java from inside our Swift application. Like here, we're using the JDK's file reader and passing it to the CSV library that we just imported. What's more, we can even use Swift's for each loops directly on returned Java collections. We've learned how SwiftJava makes use of both Gradle and SwiftPM to provide a great user experience. We're able to import entire Java libraries without having to modify any of the Java sources. The source-generated Swift code makes use of JavaKit-provided JDK wrapper types and handles user-defined types seamlessly. JavaKit also simplifies lifetime management of Java objects by promoting references to Java objects to global references when necessary. The final technique we'll discuss today is making an entire Swift library available to a Java application. It's a very important use case because it allows us to implement crucial core business logic in Swift and use it in all our applications and services, regardless if they already adopted Swift or not yet. We did mention earlier that interoperability needs to go both ways. It's worth really internalizing that by making the Java to Swift direction a great experience, we enable more projects to use Swift and have a good time doing so, which is an important social aspect of introducing a new language to a codebase. Now, if we were to approach exposing a whole Swift library using the previous techniques, we'd have to write lots of wrapper functions on the Java side. For a few functions that's fine, but if we're talking about a whole library, it's time to consider a different approach. Similar to what we've done in order to expose a Java library to Swift, now let's make calling Swift as seamless and easy as possible for Java. We'll do so by wrapping all types of our Swift library with Java classes and distributing it all together as a Java library. This time we won't be using JNI at all. Instead, we'll be using the new foreign function and memory API that got stabilized in March last year and is now available since Java 22. This API offers improved control over native memory and how native calls are formed. In some situations, it can be used as a JNI replacement. By making use of these new APIs, we're able to build a very deep integration between Java and Swift's runtime and memory management. This would not have been possible otherwise. This results in improved safety and performance as we make native calls from Java. For this example, let's use this Swift struct type that represents some business object I'd like to expose to Java. It is a value type and therefore does not have a stable object identity, which isn't something Java objects can express. Because of that, we will have to be careful dealing with this object in Java. It also has a public property, an initializer, and some methods to operate on it. In order to expose this type to Java, we'll be using the SwiftJava command line tool again. However, this time, we'll use it in a slightly different mode. We're provided a Swift input path and output directories for the generated Swift and Java sources. The tool will then take all sources from the input path and generate Java classes which serve as accessors for the Swift types and functions. We will also generate some necessary Swift helper code. Finally, everything, including the Swift code built as a dynamic library, will be compiled and packaged up into a Java library. The generated Java class will look something like this. It implements the Swift value interface because it was a struct. The class contains a self-memory segment, which effectively is a pointer to the instance in the native memory. It also represents all public initializers, properties, and functions using their equivalent Java signatures. Inside these, we have source-generated highly efficient code to make the native calls using the foreign function APIs. Now inside our Java application, we can depend on the generated Java sources. In order to create and manage native Swift values, we're going to need a Swift arena, which takes care of memory allocation and lifetime of Swift objects. Once we have an arena prepared, we can just invoke the Swift values constructor, as if it were a normal Java class. Let's take this opportunity to discuss a bit more how native and Java memory resources are being managed here. First, a new Java wrapper object is allocated on the Java heap, which is managed by the JVM's garbage collector. Its source-generated constructor then uses the passed-in Swift arena to allocate and initialize an instance of the Swift value type on the native heap. Normally, value types like our Swifty business struct are allocated on the stack, but because we need a stable memory address, we allocate it on the heap instead. This allows us to safely point at this memory address from the Java wrapper object. Eventually, the Java wrapper is no longer used, and the garbage collector will decide to collect and destroy it. This will trigger a destroy of the native instance on the Swift side as well. So memory management-wise, this is safe. However, unlike in Swift, relying on object finalization like this puts a large strain on the GC due to additional tracking it needs to perform to such objects. This also results in unpredictable timing of the native Swift value being deinitialized. So while this is an easy pattern to get started, let me show you a better way to manage native memory. Instead of using an auto arena, we can use a try with resources Java syntax in combination with a confined arena type. The object allocation will play out the same way here. However, the try with resources changes how objects are destroyed. Specifically, at the end of the try scope, the arena will be closed. This triggers the destroy of the Java wrapper object, which in turn triggers the destroy of the Swift value on the native heap. This approach is much better. We don't burden the GC with object finalization, which can be problematic when done in large numbers. And we also regained the property of well-defined and orderly object deinitialization, which many Swift programs rely on. So whenever possible, try to use scoped arenas, rather than relying on the GC for best application behavior and performance. To recap what we achieved here, we were able to wrap a complete Swift library with just a single invocation of the SwiftJava command line tool. We're able to build such Swift wrapped as Java libraries and even publish them, making them simple to consume in Java projects, further simplifying Swift adoption in your teams. And by using the modern foreign function and memory APIs, we're able to tightly control the object allocations and lifetimes, even of Swift value types. We covered a lot of different techniques to work with Swift and Java today, and you can use them independently or together, depending on the specific needs of your project. Even though we're just getting started, and a lot remains to be polished and refined, SwiftJava already offers a great approach for interoperability between these languages. By using SwiftKit and JavaKit support libraries, you can write safe and efficient code that uses one language from the other. And JavaKit macros, as well as the SwiftJava command line tool, automatically generate any boilerplate that would otherwise be difficult to maintain. Finally, I'd like to invite you to join us in the development of this project. It's completely open source and available under the SwiftLang GitHub organization. There's still lots of exciting challenges to solve and ideas to explore. If you're not quite ready to contribute, but you'd like to learn more about Swift and Java, or share your ideas and feedback, the best way is to join us on the Swift forums. Thank you very much for joining me. And as for me, I think I'll get myself a cup of coffee.